Let's begin. We'll just recapitulate what we did during the last session. Uh, this was the problem which I had presented to you, which is about recovery of D-limonene from orange peels using steam distillation. And we used the same logic and procedure which was employed for understanding the liquid-liquid vapor phase behavior of hexane and water system. There were some questions which arose during last session, and they are of some generic interest because we are not doing this particular exercise only for understanding the thermodynamics and the theory behind it, but also how it applies to the actual real life problems in industry. So one of the questions which came up during this discussion was, why generate steam in a separate equipment like this, and why not directly hit the slurry pot? Okay. Because this looks like a ridiculously superfluous kind of an arrangement when there was slurry with excess of water, and one could have directly heated this particular pot for getting the necessary steam distillation accomplished. Yes?
I had a similar question along these lines.
Yeah.
Why are we using steam? Can we not use something else that can better extract the?
We can. There are several, but all solutions will have their own pros and cons. We will look at that in a very brief manner. We will not have time to go into details of such kind of process design, but at least some principles which are definitely worth discussing during this course, we'll touch upon that. See, one of the reasons is that D-limonene is an optical isomer, and it has a particular fragrance. Now it is completely modified once it racemates, and you have a mixture of L-limonene as well as D-limonene. And when D-limonene is exposed to thermal treatment, it does undergo racemization. So therefore, that is one reason why one would not like to subject D-limonene to a very high temperature, and in fact at its own boiling point also it can really break down into isoprene. So one would like to extract or recover D-limonene at as low a temperature as possible. Most of the bioactives and many other fragrance molecules that you encounter and which are used in foods industry as well as any other industry, they are thermolabile. For example, I will give you one particular molecule on which I have a personal experience because we tried to extract that, which is azadirachtin. Have you heard of azadirachtin? Have you heard of neem? Okay, neem seeds contain azadirachtin. The botanical name of neem is Azadirachta indica, and the seed contains azadirachtin. It's a terpenoid, and that terpenoid has antefidant as well as insecticidal properties, and it is considered to be a extremely good alternative to other synthetic insecticides which are not biodegradable, and therefore for organic farming azadirachtin has a very high value. Azadirachtin, when it is extracted from the neem seeds, if we extract the neem oil using hexane as a solvent, and then we try to recover the solvent and get the azadirachtin and the oil, then what happens is that the residual quantity of hexane that you have to remove from azadirachtin containing oil, you have to take the temperature to more than say about 190 degrees centigrade. There are two reasons. One is that one would not like to have any inflammable solvent like hexane in such kind of products of common use. The second reason why you have to go to a very high temperature is that we talked about thermodynamic activity. You would find it surprising, but the thermodynamic activity of hexane or many such solvents in vegetable oils actually goes down at a very low concentration. So the thermodynamic activity of hexane in oil at extremely low concentration is as low as 0.5. So what that means is that you have to raise the temperature to such a high value that you have, only at high temperature treatment you can do desolventization or deodorization, as it is called in the conventional industry. And such kind of an azadirachtin is of no use. So therefore, usually azadirachtin is obtained by cold pressing neem seeds at 35 degrees centigrade. In fact, you have to take care that during cold pressing, because of friction, the temperature does not shoot up to 45 degrees centigrade. Then azadirachtin will get degraded. Now it is not effective at all. I am just telling you this because you must have this such kind of concerns at the back of your mind when you are choosing a particular process. So D-limonene is thermolabile, and therefore direct heat is something that you cannot really afford for removing D-limonene. There was another question which came up. Huh? Steam jacket can be used. Yes, steam jacket can be used for this, and because you can control the temperature to around 100 degrees centigrade, no problem. There was another question which came up. Yeah. Yes. No, no, no. You can vaporize D-limonene if possible at a low temperature by some other means. Not simply by taking it to its boiling point.
So I wanted to ask how much of the extraction is because of entrainment and how much of it is because of BLE?
Because of
BLE or entrainment.
what do you mean by entrainment? See, generally in azeotropic distillation, you call the solvent added as entrainer. Okay, so this is not physical entrainment. This is vapor phase entrainment. Huh? So I am not talking about physical entrainment here, right? It is not droplets which are going, but it's a vapor which is being entrained into the vapors of water and then taken out. Okay, so there was another question which was raised, that what is the need to distill of limonene along with water and like a fool then separate limonene from water by gravity settling? Why not allow the slurry in water to gravity settle and recover top layer of limonene? So it's a very simple, straightforward question, and I think it is a reasonable question to ask. So I am just giving you practical reasons for what it happens. So this is an illustration of the efficacy of different methods for recovery of oil from coconut. Okay, so you can treat this coconut kernel as similar to the orange peel. Fine. Now coconut kernel, there is a method by which you can remove virgin coconut oil by boiling it with water. Now the oil content in coconut is about 65%. The recovery by this particular process is only 61% of this 65%. So the residual concentration of oil in the copra cake, which will be the residue, will be something like about 25%. It is way about 2%, which is already present in your orange peel. There is another method, expelling. Okay, so here you cold press it. Now the recovery goes up slightly, so 73% of 65%. That will leave about 18% of oil in the copra cake. You can do multiple expelling also, but you can never get below about 8% of residue. The third possibility is, you were asking, and which is a good possibility, which is using a oil, a solvent which has got high affinity for the oil, which is hexane, right? So you get in first one stage hexane extraction something like about 83% recovery. and therefore the residue will be 11%. You can do second stage, you can do third stage as well. And if you do third stage, 3-stage extraction with hexane, 99% of the oil would be recovered, the residue would be 0.3. So D-limonene can be extracted by using hexane because the concentration available is 2% and this is 0.3%. So therefore then you will be able to extract. But so therefore all these other methods, they are useful only when you have the oil concentration or the essential oil concentration is much higher. Fine. The problem with hexane extraction I just mentioned to you, there are 2 or 3 problems. One problem is that desolventizing the product that you get does require a high temperature operation. In fact, in solvent extraction industry, you would have falling film evaporators in which final stage, in fact, steam is used to desolventize the oil because the residual hexane has to be removed. Otherwise, the clothes cup flash point is below your normal room temperature. So it becomes dangerous also. So all those things are there, and therefore second thing is hexane extraction is an expensive operation because depending upon the kind of plant that you have, you can get anywhere between say 0.5 to 3% of loss of hexane per cycle, and that is too expensive also. So all those reasons are there, fine. One related to quality of the material that you have, second is related to the expenditure that you will have to incur. So therefore, generally essential oils or such kind of bioactive materials, one would like to make use of a molecule like water if the molecule under consideration is resistant to water, because otherwise if it gets hydrolyzed then you cannot use water. Steam distillation becomes one of the preferred methods of recovery of such kind of bioactive molecules. Okay, so these 2 questions came up, and I think they should be at the thought process behind the selection of the method for recovery of the orange oil or the D-limonene must be shared with you. That is why I shared these 2 slides with you. So what we did was, we first looked at the possibility of really whether steam distillation is possible or not. We used the Hansen solubility parameter diagram, and more the distance between the solvent or any kind of a process aid and the molecule under consideration, the likelihood of getting such kind of phase equilibria is larger. And in our case, therefore, we can safely say that D-limonene, which has a chemical structure which is very similar to, because it's a terpene, very similar to these kind of hydrocarbons, and the distance between these 2 is so large that it is amenable for a liquid vapor equilibrium. Fine. So this is the reason why we said that we can go ahead with that particular proposition. The next thing was that we actually sketched a schematic 2-component vapor liquid diagram for the system. This is essential if you want to really make use of minimal data to make a kind of a judgment about and hypothesis about what is the result that you are looking for. Now one question did come up. Somebody asked me, you usually draw such kind of a liquid vapor phase equilibrium diagram which is almost symmetrical like this. Why did you show an asymmetrical diagram? Okay. Now since we have already carried out the exercise with hexane and water, it is very clear that the boiling point plays a very important role in where this will. So if this boiling point is somewhere here and this boiling point is somewhere here, okay, generally this kind of a slope that will depend partly on the latent heat of vaporization, but it may not really change much. So generally when such kind of curves are raised, so you will get a curve which will be parallel to this almost, and this curve, it will come down like this. Okay. So intuitively you can make a judgment that this is likely to be an asymmetric kind of a phase diagram. So somebody raised this question, and this heuristic judgment one has to really bring to bear whenever you are solving an industrial problem. The next question was the dew point compositions that we estimated, okay, and you have completed this exercise, I hope. This is the kind of a phase diagram that you get. So you have an azeotropic composition corresponding to about 0.91 mole fraction of water, and the temperature at which it happens is about 98 degrees centigrade. So this is the dew point in equilibrium with the limonene nearly pure liquid, and this is the dew point line in equilibrium with water. Another observation one must make, at this particular line for water, for example, it is not altered by which is the other Secker component present in this pair. So whether it is hexane or limonene or something else, this line would be just the same, okay, in this analysis, which is a slightly approximate analysis, but this line would be same. So therefore, as far as D-limonene is concerned, instead of water, you use methyl alcohol, okay, then the methyl alcohol line would be somewhere here, but this line would remain the same. Fine. So this is very important to really grasp. Having done that, then we looked at the normal template for mass and energy balance. We actually presented all the data which was there available to us, and then we'll simply going from the mass and energy balance around the stage 1 and stage 2, we could fill up all the gaps available, and then so the final answer was that the total quantity of steam required for distilling of the limonene in 100 kilograms of orange peel was about 28.7 kilograms. Did you get that answer? Did you go up to there? It is important to go through this because, you know, only when you solve these problems yourself, you will become familiar with it, and these concepts will get ingrained into your process of thinking. So this is the answer which I got. I have uploaded this entire set of slides on Moodle already, so you can have a look at those. The next stage is really we would like to have a treatment which is suitable for solid-solid liquid thermodynamic phase equilibria, because those kind of problems are quite common in a large number of different applications involving what is called phase change materials, okay, and we are going to have such kind of problems solved in the classroom. So this is one system like that, which is water and ethylene glycol, which is normally employed for, say, for example, de-icing of aeroplane wings. When they land in a snowy terrain or before taking off, the de-icing has to be done, and for which the water ethylene glycol kind of a mixture is used for de-icing of the deposited snow on aeroplane wings. So such kind of a problem and such kind of products, if we want to develop, we need to have these phase diagrams, and their quantitative understanding is very important. Now, can we construct such kind of a phase diagram like we did it for the liquid-liquid vapor? We simply cannot. The reason is that in vapor-liquid system, the partial pressure in the vapor phase serves many purposes, okay. Number one, it is also a measure of the composition in the vapor phase. It is also a measure of the chemical potential of the vapor phase. It is also shows us proximity to condition of boiling. So boiling point is also something which is very easily interpreted in terms of the VLE diagram. So this approach is really not extendable for the case where you have solid, solid and liquid in equilibrium. So we are in search of another method which may be applicable both for vapor liquid liquid as well as solid solid liquid. Okay. So that is the kind of a exploration we are going to do in the session today. Look at this diagram, something we have already covered, that at equilibrium, so this is the phase diagram, you have the component A here in pure liquid phase, component B here in pure liquid phase. So these green lines represent that liquid phase component, and in equilibrium with that you have Ya, which is the concentration of the vapor in equilibrium with this nearly pure liquid. We know at equilibrium the chemical potential of the ith component, here the I is A, is equal to chemical potential of the vapor of the ith component. Okay. Now let us apply this equilibrium between L1 and vapor for a component A at any temperature T. So this is true for any temperature T. Okay, you take any temperature T here, and at the tie line this relationship is valid. Fine. Now for the L1 phase at any temperature T, L1 phase at any temperature T, the chemical potential of A in the liquid phase here is equal to, this we have seen here, the molar Gibbs free energy of A in the liquid phase for the pure component plus RT ln activity of A in the liquid component 1. Okay. So for nearly pure liquid, since activity is equal to 1, therefore this relationship, in this relationship this particular part really becomes 0, and therefore the chemical potential of A in the liquid phase is equal to the Gibbs molar free energy of A in the liquid phase, which is written here. Fine. So this is something which is true. So chemical potential on this entire line is like that. So the chemical potential on this entire line is mu L1. Fine. Chemical potential is not constant at different temperatures. So don't make that mistake. Chemical potential is not constant on this whole line, but at given any particular temperature, chemical potential of that component is equal to the molar Gibbs free energy. Fine. It is varying with temperature, but this is an identity. This is not an equation. Now, for any nearly pure liquid phase at any temperature and given P, this we have already said is equal to 0. So what we said in the previous slide is diagrammatically represented here. So this is the chemical potential or the molar Gibbs free energy of A or I. In the solid phase it goes like this, with temperature it decreases. For liquid phase also it goes like this, with temperature it decreases, and gaseous phase also similarly decreases, only the slopes are different. So you take any point on this liquid phase, okay, which is on that vertical line, this point is given here. So the chemical potential of this liquid is the molar Gibbs free energy of that liquid given on this particular point. Fine. So this is relatively straightforward. Now, if the vapor phase is in equilibrium with the gaseous, with the liquid phase, then obviously the chemical potential of A in the liquid phase 1 has to be equal to the chemical potential of A in the vapor phase. Okay. So this is, and since the vapor phase is also nearly ideal, generally the vapor phase chemical potential is written very similar to the liquid phase chemical potential, which is equal to molar Gibbs free energy of A in the gaseous phase plus RT ln P asterisk. P asterisk happens to be the ratio of the partial pressure of that particular component in the vapor phase divided by reference pressure. Generally, the reference pressure is taken as the reference state is 1 atmospheric pressure. So, if you are carrying out generally an operation in atmospheric pressure, in that case this P star A really becomes equal to in fact the mole fraction, because the total pressure itself is only 1, and here so the partial pressure divided by total pressure, it will become equal to 1. So, this is the kind of a relationship that you have for the chemical potential of A in the vapor phase, comprising two terms, one which is the molar Gibbs free energy of A in the gaseous phase, which is this gas phase. So, this is the value, okay, plus this correction. So, this plus this is the chemical potential of A in the vapor phase, fine, and this is at a given temperature. So, at different temperatures it will be a different value. This value would be different at different temperatures depending upon where on this line you are, or where at what temperature you are looking at that value. So, this is again explained here, that the same thing as I said, the P asterisk is nothing but the partial pressure of A divided by the P standard, which is dimensionless. Moreover, for atmospheric pressure operation, P asterisk is equivalent to YA. Therefore, for atmospheric operation, you get the chemical potential of A in the vapor phase is equal to Gibbs free energy, molar Gibbs free energy of A in the gaseous phase, which is this value, plus RT ln YA, which is the mole fraction of A in the vapor phase, which is considered to be ideal, and total pressure is 1 atmosphere. So, this is very pure simple algebraic manipulation. Now, if you do this manipulation, then you can equate the two terms. The chemical potential in the liquid phase has to be equal to the chemical potential in the vapor phase. Hence, this chemical potential in the vapor phase is equal to the chemical potential in the liquid phase. If that is the case, then this can be then opened, and you have ln Y, which is the ln of mole fraction of A in the vapor phase, equal to the chemical potential of A in the gaseous phase minus chemical potential of A in the liquid phase at any given temperature T, okay, and Y becomes exponential of this particular term for a given T and for atmospheric pressure operation. So, all we have to now do is find out what is the value of this term at different temperatures. So, if we know what is the value of this difference between the between the molar Gibbs free energy of A in the gaseous phase and the liquid phase at any given temperature, you can find out Y. So, that is a very simple kind of a information we can extract from this elaborate but very straightforward algebraic treatment. So, YA in equilibrium with pure A can be estimated if we know delta GAL at different temperatures, fine. So, this is again schematically shown here. This is the liquid phase, this is the gaseous phase. So, what we are interested in knowing is at a given temperature T, what is the difference between this point and this point? That is this delta GAL, which is the difference in the chemical potential or molar Gibbs free energy of A in the gaseous phase and the liquid phase. If we know that, we can find out YA. Okay. So, all we have to find out is this difference now. And how do we find out this particular difference? We take help of certain straightforward observations. We can see that this difference becomes equal to 0 at boiling point. That is why chemical potential of the liquid and vapor becomes equal at the boiling point. Fine. So you can, if you want to find out this difference, one would like to start from this boiling point and find out how much deviation is going to be there in these two lines starting from this boiling point. That is why boiling point becomes extremely important reference point. This is diagrammatically shown here. Okay. So this is the boiling point temperature. Fine. Now at any given temperature T, supposing this is T, this is TB where the two are identical. This is T at which this is the liquid phase molar Gibbs free energy. This is the gaseous phase molar Gibbs free energy. So the difference between the two, okay, is going to be this delta GL. Fine. So at any temperature, at T equal to TB, G and GL are identical, which is this particular point. So for any phase G or L, total differential of the Gibbs free energy for the component is equal to minus S dt plus VdP. We have seen this earlier, and VdP is identically equal to 0 when pressure is going to be constant. So therefore we are not interested in this particular term, but we are certainly interested in this particular term. So if we know the dG for liquid and dG for the gas, the difference between the two dGs is the one which is the value of interest to us, which is this. Fine. So therefore dGL is equal to minus the entropy of L dt, and dGg is minus entropy of G multiplied by dt. So when you go from here to here, that difference is this, and when you go from here to here, that difference is this. So if you subtract the two, you will have, and you rearrange that, and you get the T on the denominator here. So the two differences are really nothing but the difference between the entropy of liquid phase and the entropy of the gaseous phase. So the difference in the molar Gibbs free energy of any component in the gaseous phase and the liquid phase and its derivative with respect to temperature is equal to the difference in the entropy of the two phases. And entropy of the two phases is nothing but the enthalpy divided by T. Fine. You can now integrate this. You can take the dt here and you integrate, and you will get an ln term here. So once you integrate it, that delta GL, so this G is nothing but the molar Gibbs free energy. This G stands for the gaseous phase. This L stands for the liquid phase. So this delta GL is equal to ultimately the enthalpy for transition from the liquid to gaseous phase into ln T divided by TB, because you can start the integration from this particular point where the two are equal. And ultimately what you get is this particular expression. Okay. So delta GL is nothing but the enthalpy of phase transition given the TB here, and for any temperature T. So you take any temperature T, and this expression are identical. Now here one assumption is there that the latent heat of vaporization is constant during this integration, okay, which is not necessarily true if you go to a very large difference in temperatures. Fine. And therefore you get into a problem. I will show you where you get into the problem, but generally wherever you can assume that the enthalpy of vaporization is relatively constant in the temperature range of interest to you, in that case this expression is fairly good. So therefore YA estimate is nothing but this alpha A is equal to this particular difference, and this expression is nothing but this expression. Okay. So YA, the mole fraction of A estimate, is equal to exponential of this term. Thus, Y estimate can be evaluated for different T at a value of T smaller than the boiling point for any component in equilibrium with respect to nearly pure liquid phase. So we have got an expression now which is fairly straightforward, simple, and it is not influenced by the presence of the other component here, because they are two completely immiscible liquids, and therefore you are now looking at a immiscible liquid in equilibrium with vapor, and this is the vapor phase composition in equilibrium with nearly pure condensed phase of that particular component.
Sir, this
Yeah.
Yi into T also gives you the vapor pressure as a function of temperature.
Which one?
With the same expression,
Huh.
if you multiply Yi into T,
Huh.
then you essentially
You can get
the
partial pressure. Yeah, vapor pressure. In fact, the Troughton's method to predict the vapor pressure is this. So you can extend this method in reverse manner to predict the vapor pressures. Yes. So you will actually see this, when we go in a convoluted manner, how this happens. So a heterogeneous azeotrope is encountered when you estimate the for L1 and L2, estimate the concentrations in terms of one particular component. Say for example, here 1 minus Ya is really Yb. So for L1, what is the Yb, and for L2, what is the Yb? When the two become equal, then you get the azeotropic composition, because the two curves intersect there. So this is what exactly is really shown here. What I would suggest is, this is what happens. So when you do those estimations, you will get these kind of curves. Say for example, this is ZB. So this is in terms of B, we have plotted everything. So this is the dew point line for B in equilibrium with B. This is the dew point line for A in equilibrium with A, and this intersection is the azeotropic point. It's a fairly straightforward kind of a estimation, but just to become familiar with it, we will complete this small exercise. So complete the two tables, and then graph paper is given, so you plot the graph. We'll do something more on the same graph paper later. I have given already the formulae involved as a hint to all of you. Yeah.
Here, conversion is given as 272, so we should take 272 or should we take 272?
Which conversion?
Degree to Kelvin. Although it will not affect much.
No, समझा नहीं मुझे.
डिग्री से करने में 273.15 जोड़ते हैं ना.
हाँ.
लेकिन यहाँ पे 272.8 जोड़ रखा है इन दोनों में.
272.8.
माइनस करके देखा इसके लिए.
क्या हो रहा है?
तो 272.8 है.
हाँ.
लेकिन 273.15 होता है ना.
That is boiling point, ना?
No, to convert degree into Kelvin, we add 273.15.
Correct.
But here, from given data, if here we are adding 272.8, not 273.15.
It is a mistake, I guess.
So it is mistake, or we should take what is given for conversion.
मुझे समझा नहीं पेपर में।
कॉपी का मतलब हमें पता होता है ना कि 0 डिग्री 273.15 केल्विन होता है।
हाँ
तो जब भी हमें कोई डिग्री दे रखी थी टी, तो उसे केल्विन में करने के लिए 273.15 जोड़ते हैं।
हाँ, sometimes they put 272.8 also. That is the problem. You take anything, doesn't matter. Somebody pointed out there is a small confusion in the data given, where the melting point of ice is taken as 272.8 and not 273.15. So you can use the actual today's standard, which is 273.15. आपका हो गया? हाँ? प्लॉट नहीं किया, प्लॉट कर लो।
Is something wrong?
Something wrong, yes.
It should mean at 68.7.
नहीं, and then the shape also is not right.
Okay.
जरा चेक कर लो, हाँ? Your interpretation may be wrong. Where is your temperature? Temperature is here, na? So then shapes are right.
Oh, okay. We
Huh?
see this here.
Temperature is the y-axis.
Got it.
So this is right. So just draw this line, this line. This is your okay. Now it is important to draw, then physically it ingrains into you. आपका हो गया? Very good. अब प्लॉट करो ना। हाँ? Do it with your own hand, then only it will get into your thinking process. आपका ये कितना आता है?
The azeotropic boiling point.
हाँ,
So this is between 61 and 62 के बीच में आ रहा है.
हाँ बराबर है। आपका azeotropic पॉइंट कितना आता है? करेक्ट, हाँ 61.5।
Yes, 61.5.22 is.
ठीक है, approximately. So you remember what was the value in the previous vapor pressure से किया था?
For what? Value for?
We did it for hexane water, ना?
Yeah, they were 0.21 and 61.5.
हाँ, so it was a very different method. कितना टेम्परेचर आता है आपका?
61.
करेक्ट, ठीक है, गुड। प्लॉटिंग कर लो जल्दी। हो गया आपका? हाँ हाँ, करो जल्दी करो। Because nothing gives you a physical insight more than actual diagram. Numbers don't give that. हाँ, बन गया? गुड। कितना टेम्परेचर कितना है?
61 point something.
Correct. So we did it last time with vapor pressure. The exercise number 6 was with vapor pressure. So we had to use vapor pressures at all the temperatures, etc. Here only 2 values give you everything. आप प्लॉट करो. क्या हो गया? नहीं करो. You have to. हाँ, that is important. Improving your concentration.
To do it in the y-axis, I did in the x.
Huh?
I have to basically do this in the y-axis, that the temperature thing.
Temperature you put y-axis.
I have
Yes.
done it in the
It's okay. You turn it.
It is a different kind of graph now.
नहीं ऐसा कुछ
Second
नहीं.
quadrant. Okay.
So what? क्या है आपने बनाया ग्राफ?
So just completing these.
जल्दी जल्दी करो. आप प्लॉट कीजिए ना जल्दी. हो गया ना? वेरी गुड. कितना आता है टेम्परेचर?
Approximately, sir, 6162.
ठीक. So some people have already been able to complete the computation and plot the graphs. What I am giving you next is this data, which was the problem, the TP exercise 6. Okay. Here we estimated the concentrations of the vapor phase or the dew phase line or the dew point line using vapor pressure data. So on the same graph, please plot these points also, which you had predicted earlier using a different set of data, which was vapor pressure data. So फिर से plot करके देखो on the same graph, same scale, same graph. So Y water you take on the x-axis. Huh? Just plot and find out how much is the difference. क्या हो गया मैडम? हो गया? कितना? What temperature you got? जल्दी करो. हाँ? You know, it is important. We have forgotten the what we do in school days, but I can tell you one thing, that even when you do PhD, most of what you learn during the school days becomes more useful than anything else. Yes.
Somewhat around 61 point.
Yes, correct. Huh? No, but you know, you will get lot of data in life in this graphical form. Interpreting that requires practice.
Yes.
So you do it, it will be useful to you.
Yes, sir.
So now you can plot on the same graph paper this information which we had generated using the vapor pressure data.
I mean, that is almost equal. So
Yes.
it would just repeating the same lines.
Yeah, but you know, that's a revelation. Na? It is important, you know. We have come from entirely different approaches. Plot किया ये? So, हाँ? Overlapping ना? Confusion gone?
नहीं है इस मेरे में
क्या हो रहा है?
ऑप्शन कैलकुलेट नहीं हो रहा है
अच्छा.
और
Do you need my help? नहीं. हो गया? Both are overlapping. This is how the data from the two different approaches looks like. Okay. So this is in green, blue, yellow and black. They are almost overlapping each other. So by two different methods for hexane water system, now we have been able to predict the vapor liquid equilibrium. Okay. It is something when actually we see it, it becomes quite surprising. One has to be cautious, however, while using the latent heat and boiling point data over a extended temp. So if the two components, their values of boiling point are extremely different, then you may have a problem that this particular curve, if this boiling point goes here, then it might go even outside this. So therefore, that method does not work when the temperature boiling point differences are huge. But generally otherwise, you get the boiling point differences are closer. Both the methods work well. And in fact, what it means is that the latent heat of vaporization and the boiling point, these two data points were able to predict in indirect manner the vapor pressure which we use for the earlier exercise. So that is a a method for even predicting the vapor pressures which Rochesh was mentioning. So once having accomplished this now, we are almost ready to look at the solid liquid equilibrium. So we will take that in the next session, but I would like to know if, until now, because we have covered lot of ground and lot of principles. Number one, for an extremely non-ideal system, which normally is not handled in the regular classes of thermodynamics for vapor, for phase equilibria, we said that we in fact find it extremely easy to predict those phase equilibria by making certain assumptions, and they seem to be quite reasonably accurate. Fine. And two or three different approaches converge together to give the same information because they are internally consistent. So that reinforces our faith in the thermodynamic treatment which has been developed by our predecessors. So we will now use this particular method for the solid liquid equilibrium, because then we will be able to solve some problems related to the phase change materials, and which kind of products are becoming quite common these days, even for say energy storage, etc. Okay. But if you have any doubts until now, you can raise.